Good afternoon. Okay, this is Physics 204, August 1st, 2023. This is in lieu of meeting synchronously today. This will be a comparatively short video. There may well be more video material posted a little bit later. That video material may be from a prior semester, but we'll pick up where this leaves off. There may or may not be over the next 2 days. There'll be various videos. Over the next few days, there'll be various videos and some degree of synchronized interaction, but the total amount of video that will be posted and for which you will be responsible will not exceed a total of 5 hours, if that makes sense. And it may be slightly less. Anyway, this video, let's put up the board here. This video is to pick up where we left off yesterday regarding the wave equation that we just derived, the one-dimensional wave equation. And it's what we're going to do right now is do a brief overview of what it means to unpack the wave equation. In other words, what is the wave equation asserting? It is telling us mathematically what it means to be in wave motion. But we're going to look at that in a little bit of detail. Here comes the board. And after we slightly unpack the relationship being asserted by the wave equation, more specifically, after we compare that relationship to the relationship being asserted for simple harmonic oscillation, then we are going to make some comments about the speed of a wave and show how the character of wave speed leads us to a very, very fundamental and slightly perhaps surprising phenomenon known as the Doppler effect. Our goal over the next couple of days and in the homework assignment that's actually due tomorrow, the homework that's really on the docket right now is all about the Doppler effect. Somewhere in all of this, you will have looked at that in lab. The Doppler effect is fundamental to the universe, and it is on our final exam. So the ultimate problem-solving goal of anything I say today and tomorrow, the ultimate problem-solving goal is to be able to solve for 4 distinct cases of the Doppler effect, 4 distinct cases, and to be able to compare and contrast the results, the findings for those 4 cases. That's the ultimate purpose of all of this, is to be able to navigate our way through a Doppler effect problem, all 4 cases. So that's where this is all heading. We're not going to get to all of that in this video, but this video lays the groundwork for that. Okay, so we've got the board, so we're going to get going here. Okay. So the top equation, we'll get straight to it. The top equation is the one-dimensional wave equation. It is a second-order partial differential equation. It is the one that we derived yesterday by taking 4 distinct partial derivatives of an expression. The original expression that we have, and we're not going to go back talking that, but watch yesterday's video or whatever. The original expression was an expression meant to describe a collection of identical oscillators. It was meant to describe a collection of identical vertical oscillators spread out equidistantly in horizontal space and staggered in phase by a constant step. Staggered in phase according to their position in horizontal space, right? So we had this one expression that described a whole bunch of oscillators that were all doing the same thing, but all in a pattern of phase delays or phase head starts. We ultimately said that if we set up this collection of appropriately phase staggered oscillators, then what we actually have is wave pulses propagating back and forth through the horizontal space of these vertical oscillators. We took four partial derivatives of that multivariable function, and we got this thing on the top of the board. Right? This thing says what it means to be wave motion. It is a function of two variables, horizontal space and time. We're going to flip the page. We're going to start talking about it. Let me make one more. Well, okay, let's flip the page and talk about it. Let me make one clarification. I keep using the x-axis to mean horizontal, and I keep using the y-axis to mean vertical. It doesn't actually have to be that way. I think it's the easiest way to picture this, especially at the beginning. But really, it might be even better to just think of the y-axis as the axis of oscillation. The y-axis is whatever axis each one of these oscillators is going back and forth within. And the x-axis is the axis along which they're all arranged, and the axis along which ultimately we see this immaterial, ethereal, energetic, informative pulse flowing, right? So ultimately, by x, I mean the propagation axis. You might want to write that down. Maybe I'll write that down. Hard to write this without. Ultimately, by x, I don't care. In other words, this whole thing can be turned on its side, and it's still all true. And it can apply to other phenomena that don't look literally like masses on springs and aren't literally arranged horizontally and vertically like this. But by x, I ultimately mean the axis along which the immaterial pulse flows. And by y, I ultimately mean the axis along which each one of these little particles oscillates. I'm going to leave that there. Okay. All right. So what does this wave equation, this second order partial differential equation mean? First of all, remember, when we created wave pulses remember, a wave pulse is something that actually cannot be fully captured in one two-dimensional graph, right? If you want to think about wave pulses in terms of traditional Cartesian graphs, you actually have to make two of them, as you did in Lab 3, and as is happening up here at the top. What I'm really trying to say up here at the top is, please always remember that an oscillator is not a wave. An oscillator is not a wave. An oscillator is the fundamental ingredient from which we build waves. An oscillator is a particle undergoing a series of trajectories through space, right? An oscillator is traditional mechanics. It's material, it's particular, it's discrete, it's identifiable. An oscillator can be described by that second graph of the top two graphs. The second graph, it's something that, like a vertical oscillator, is something that goes back and forth along the y-axis as time flows, right? So that second graph is not a wave. That second graph, in effect, is an oscillator. The first graph is also not a wave. On the one hand, I'm saying a wave is not an oscillator. A wave is built from that, just like a brick house is not a brick, right? But also, and then this is a little bit more surprising, or sometimes, I'm also saying a wave is not a wiggle. That shape that I've drawn on the top of the whole page, that thing, which people think of, oh, that's a wave. No. That's not a wave. That is a snapshot of a wave, right? That is one moment, t equals t naught, any moment you've chosen to freeze time and picture a big string or some one-dimensional continuous medium. At any moment in time, it's in the shape captured by that first graph. So that first graph, the top graph on the sheet right now, right? That is y as a function of x at some value of t that's held constant, right? That is y as a function of x. So that's a wiggle. That is a time slice of a wave. And then the second graph is an oscillation, that's a space slice of a wave, so to speak, right? That's what y is doing as a function of t if we picked one horizontal position and held it fixed, as you did in lab 3, right? Those two graphs together constitute a wave. The last way I'm going to put it, I mean, I know, again, this is one of those things that like it makes so much sense once it makes sense that it like seems stupid to keep saying it, but it doesn't make sense until a bit, or I'm trying to break down a misconception. The misconception is that we spent all this time on oscillation, not to say that oscillations are waves. No, we need oscillations for waves. An oscillator is not a wave. But also, I want to say a wiggle is not a wave. What a wave is the two ideas being put together and occurring somehow almost magically at the same time. A wave is a bunch of time oscillators arranged cosinusoidally in space. Or you could say the other way around. You could say a wave is that first picture. It's a wiggle that is itself oscillating in time. You see what I mean? Both together make a wave. A wave is, by definition, perpetual motion through space and time, perpetual change through space and time. So the equation that captures what is necessarily true of a wave is this middle equation in the board, right? It says that the second partial time derivative, okay, so it says that the second partial time derivative is everywhere and every when directly proportional to the second partial space derivative. It says that the anywhere and any when you look, the second partial time derivative is equal to a constant, granted a complicated looking constant, but a constant times the second partial space derivative, right? I mean, let's be sort of clear here. Maybe like this. Well, yeah, I didn't want that constant. Okay. This whole thing here, as complicated as it looks, is one big constant, right? And the other two chunks, as complicated as they look until you get used to them, they're each just a second derivative, right? So we're saying some kind of second derivative is equal to a constant times some other second derivative. We're saying that some kind of second derivative is a directly proportional to or a linear function of some other derivative. Now, that should seem somewhat familiar, right? I mean, I know the more deep we go with all this notation, the more, in a way, complicated these things can look. But really, I had a little plug here for math again. If it looks complicated, which I sympathize, if it looks complicated, it's because a lot of the symbols are new and are Greek or something. But the more you get used to the symbols, the more you start realizing that actually it's remarkable how simple this expression is. I don't mean it's easy, but I mean, like, there's actually a huge amount of information packed into a very small space. I mean, what I'm trying to say really is to act, these videos are so long and I'm so verbose, both partly because DNA, because I'm me, but partly because English is not the most economical or efficient, elegant way to express all of these ideas. Like, the truth of the matter is, there's all these symbols together is just a simple package. In effect, this thing is just saying some kind of y equals some kind of m times some kind of x, and b is 0, right? We're just saying two things are proportional to each other. The two things happen to be derivatives, which are a whole concept. But once you get used to them, then there they are in that package. Now, I'm saying this package of proportionality should be somewhat familiar, because if we now go down to the third graph on the page, the third graph on the page is remarkably similar to the second graph on the page. The third graph on the page is the graph of just one of those vertical oscillators, right? Which honestly is also what the second graph is. But the third graph, let's imagine we don't even have this whole assembly. We just have a mass going up and down on a spring from the beginning of the semester, from homework 1, etc. So we just have this mass going up and down on a spring. Now I'm keeping it in the vertical axis. So remember, we have been saying that our dependent variable could be like any old thing. So let me keep it as y. So I'm imagining one spring going up and down in vertical space. And going up and down in vertical space as a function of time. So if we're talking about one spring, then we just have y as a function of t. Let me clarify that too. Like this equation, the top equation, this was y is some function of x and t, but here we have just y is just a function of t, right? So first of all, I can drop that partial differential notation, right? I can go back to regular ordinary derivatives because there's only a function of one variable, right? So this was our equation, our differential equation for simple harmonic oscillation. And what did it say? Okay. Well, in brief, what it's, and please, again, this is where, right here is where you maybe write some things down that I'm not going to write down. In fact, I'll also say, since we said the assignment for this, what you have to do to get all the rest of the 8 points for this is you have to jot down one thing that you think makes sense that you get from this lecture, and you're supposed to jot down one question you have for something that you need to hear more about that doesn't make as much sense, right? So, I mean, here's what I'm going to do right now is going to fall into one of those two categories for all of you. Like, I would suggest writing down what I'm about to say. I'm not going to write it down, and then either you'll use it as an example of something that's totally clear, or you use it as an example of something you need to hear more about. But here's what I want to say. If you look at a simple harmonic oscillator, a mass on a vertical spring, the left side is the second derivative of y with respect to t. In English, that left side means the acceleration of the mass along the y-axis, right? We've said instantaneous acceleration by definition means second derivative of position with respect to time. So the left side is talking about acceleration. It's saying what it means to be elastic, what it means to be a harmonic oscillator is that for any point in space and time you pick, the rate at which, here it comes, the rate at which the mass accelerates back to the equilibrium position is equal to there should be a negative sign there too. Oh my God, I'm so sorry. Wait, there should be, if you caught that, you can write that down too. There should be a negative. If you even write down as your takeaway that you caught that I was missing a negative sign on the second equation, and then I put in at some point, that will definitely show you're paying attention. Anyway, there should be a negative sign here, right? Like Hooke's law, like every equation like everything we've done for the whole first unit of this. Sorry, there should be a negative sign in that harmonic oscillation equation. Anyway, if what it's saying is at any point in space or time, the rate at which the mass point accelerates back to the equilibrium position is equal to a constant times a negative, and negative means back, equal to a constant times what? Times the displacement from equilibrium position, right? So in English, what oscillation means is you are a mass point, you are a zero-dimensional object that has been displaced along a one-dimensional axis some amount of space from an equilibrium position, a home spot, which is also zero-dimensional, right? So you're you're a point, you're a mass point. You're far away from your home point called equilibrium, called y equals 0, right? Or I keep doing it horizontally, vertically, whatever. You're far away from your home point. The rate at which you accelerate back home is directly proportional to how far away you are from home, right? This is what elasticity means. The farther away you are, the greater the restoring force, the greater rate at which you accelerate back home. I'm going to say it one more time because I want to contrast that with what it means to be a wave, or I want to compare it, both. The rate at which the mass point accelerates back to the equilibrium point is directly proportional to the mass point's displacement from the equilibrium point. The rate, so the mass is a zero-dimensional point. The equilibrium position is a zero-dimensional point. there is a one dimension of displacement between the two, the greater the one-dimensional displacement between the mass point and the home point, the greater that one-dimensional displacement, the faster the mass point accelerates back home, right? And again, it's another one of these things I'm probably making it sound more complicated than you probably already understood it, and now you're like, why is he using all these words? Maybe. Because now, but in short, that's what it means to, that leads to harmonic oscillation. If the farther away you are from home, the greater rate at which you accelerate back home, all the way to the limiting case where if you're home, if you are the mass at equilibrium, you don't accelerate at all, right? And then if you're pulled out a bit, you accelerate a bit back home. If you're pulled out twice as much, you accelerate twice as much, right? That's what the mass on the spring system is all about. Now, look at the wave equation. The wave equation is saying something very similar, yet different. The wave equation starts on the left side with, again, second derivative with respect to time. It's a partial derivative, but that's okay. That's because we have to be partial because the whole function has more than one independent variable in it. But again, what that left side absolutely means is acceleration along the y-axis, right? So it's saying pick some point now. Like pick some point in that wiggly schmiggly medium, that long string that we all did in lab 3 to make this clear. Pick some point like right here, some particle, some little individual oscillator that's comprising the whole medium. That point is going to accelerate back home at a certain rate. What rate? Well, now we look at the right side. The rate is apparently equal to some kind of constant, a constant that looks very similar to the other constant, but not exactly the same. And it doesn't have a negative side. That's negative sign. That's okay. It's still a constant, right? So the right side has this constant, and then a constant times not just y itself, but second partial derivative of y with respect to x, right? So, okay, so here's where the distinction comes. The first thing I'm going to say is, again, it looks like the rate at which if you're looking at that big long string that's oscillating back and forth and oscillating back and forth, the thing that you made in lab 3, if you're looking at wave pulses flowing back and forth on a long one-dimensional elastic medium, right? You pick any point now in that wiggly schmiggly medium, you pick any point in space and time, and you will find that the rate that it's accelerating back home is directly proportional to what? To something. Well, not to how far it is from home, not to what. It doesn't say y on the second side of this equation. It says this whole thing, partial to y, partial x to. What is that? Well, it's a second derivative of y, right? Okay, well, what's a second derivative of y in English? Well, didn't we already say that the second derivative of y is acceleration? Let's be very careful now. What we said, if we're going to say that again, then both those terms mean the same thing and they just drop out. The second derivative of y with respect to time is acceleration. The left side derivative is the rate at which some piece of the medium accelerates back home. That's what the left side is. The right side says second derivative with respect to space. Now, what the heck is that? Look at the top graph. Pretend it's a math class now. Really, for a moment, just pretend this is old, like Calc 1. You have some graph on a y-x grid, right? You're not thinking about physics. You're not thinking about time. You're just thinking about some shape, some function, y equals some function of x. Back in math days, calculus days, what you learn the first derivative, if you're thinking about graphs and shapes, physical representations, spatial representations of things that are happening, you learn that the first derivative can be understood on a graph to be slope of a tangent line to the curve, right? First derivative is steepness, rate of change of the graph. First derivative you think of as slope of the tangent line on a graph. That's first derivative. It's how steeply the graph goes up or goes down. That's first derivative. What was second derivative in a math class? If you just looking on a graph, not in terms of time, but just in a function y equals f of x, how could we visually picture second derivative rate of change on a graph? I'm dragging this out on purpose because if this were a synchronized class right now, I would ask everybody to chat in and see if you remember what I'm talking about. Now, you can't do that here, but I'm going to give you time to think for a second. You'll know in your heart whether you know what I'm talking about or not. What I'm going to tell you, I'm going to stall for one more second. I'm looking for a word, an English word that has something to do with shape or physicality that is the word go to for how we physically picture second derivative in calculus. And I'm referring us back to calculus because I'm trying to get us away. Physics already makes certain assumptions about what the independent variable is. Sometimes in physics, the independent variable is time. Sometimes, as you're seeing now, it still could be space. Sometimes it can be both, right? But if you're just thinking abstract functions on a graph, you learned a long time ago how you can visualize the meaning of second derivative. And I'm stalling. Now, what I'm going to tell you right now is whether you're thinking of the word or not, and you'll know, I'll never know. I will predict that when I say the word, even if it wasn't the word you were thinking, you're going to go, oh, that's what he was looking for. Oh, okay. In other words, I'm sure you've all heard the word I'm looking for. The word I'm going to here is concavity. Yay, you got it right. That's awesome. Yeah. Oh, no, I know that's what you were thinking. You were thinking the other, but if I had phrased it, then you would have said that. Right. I know. Right. Okay, cool. No, you all know the word, right? Like if a second derivative is positive, then the graph we say is like concave up, like a bowl, an upright bowl that you can fit things in. If the graph at some region has a negative second derivative, we say it's concave down, like an upside down bowl, right? And if it has a 0 second derivative, we say there's no concavity at all, it's flat. Concavity is like the steepness of the steepness, not just how steep at a place the graph is, but how much the steepness is changing. So so parabolas are concave. Straight lines are not concave. They have a steepness, but they don't have a concavity. You know what I'm saying? You go right? Okay. So where am I going with all of this? What I'm saying is this graph is making the harmonic point. It's just like harmonic oscillation. It's making the same kind of physical point, only now it's extrapolating it or generalizing that physical point to a two-dimensional situation, to a higher dimensional situation. Here. Now here's why I used all those words a minute ago. Here, for a string that's vibrating back and forth, oscillating back and forth, equilibrium is no longer a point. Equilibrium is not some position, some zero-dimensional spot. Equilibrium now is an orientation. What is equilibrium for a vibrating string? Equilibrium is the x-axis, right? Equilibrium is that whole line. The string is at equilibrium when it's flat, when it's not oscillating at all, when both lab partners are just holding both ends and just standing there, right? Equilibrium is not a place anymore. It's it's not a spot. If you want to say it's a line, equilibrium is now a one-dimensional line, but let's be really clear. It's not even the location of a given line. It's not like a latitude line or something. It's the shape of that line. In other words, if two lab partners are holding a long metal string, that string is at equilibrium, whether these two lab partners are vertically enhanced or vertically it doesn't matter how tall they are. It doesn't matter where the string is being held. If it's flat, then it's at equilibrium. Right? So equilibrium now means parallel with the x-axis, or what we're calling the x-axis. That is the equilibrium axis, even if the whole bloody thing is like this, but if that's the way everybody's holding it, that axis is equilibrium. So home is now not a zero-dimensional spot. It's a one-dimensional orientation, right? And what we're saying, flatness. What equilibrium now is no concavity, right? And what the wave pulses are that are going back and forth, these crests and troughs that we're watching go back and forth, they're not objects. They are distortions, contortions, perturbations. They are bad shapes. Well, they're recognizable changes in the shape, the orientation from equilibrium, right? So what we're saying it means to be a wave is any given spot, that brown spot at the top on the top picture, that little brown spot will accelerate back home. It'll accelerate back to the equilibrium orientation at a rate that is directly proportional to what? To how concave the string is, at the medium is at that point. It's not how far away along a one-dimensional axis that point is from the spot of equilibrium. It's not that. It's not how far away it is, because that's meaningless. The place it wants to get to is not a place. The place it wants to get to is an arrangement. What is happening is that little point is a disturbance, a distortion. What we're seeing with our eye is, the string is up. There's a crest there, right? Now, there's no actual crest. That's not a thing. There's not an actual mountain there. It's just that the string is warped up. The rate at which that little piece of up warpness, the rate at which it will fall back down to flatness is directly proportional to how unflat the string is at that point. So a wave pulse is a disturbance. The rate at which the disturbance becomes undisturbed, the rate at which, so I'll say this now slowly, like in the same language as before, the rate at which a piece of the medium accelerates back to a one-dimensional equilibrium orientation is directly proportional to how distorted or concave the string is, the medium is, in 2 dimensions at that point. You may, if I say it again, I'm going to say it differently. You'll just have to play back the tape again if you want to. And it's not the exact words that matter, but I want you to see the parallel. Both of these have to do with restoration. Both of these have to do with direct proportionality. Both of these, when I'm saying both, I mean simple harmonic oscillation and wave propagation. They're both about the rate at which something is displaced. They're both about the rate at which a displacement gets corrected is directly proportional to the size of the displacement. But the big difference is that simple harmonic motion, the displacement is purely one-dimensional. One spot is too far away from another spot. But in waves, we take that exact concept and we hike it up by one more dimension. In waves, the displacement is really a disturbance, a disorientation, a distortion, a perturbation. It's a misshapenness. The rate at which at minimum, a two-dimensional misshapenness flattens itself out into one dimension is directly proportional to how misshapen, how unflat it is. So what it means to be a wave is, if I stand back, if I'm looking like, oh, that looks like a wave, like we all recognize it visually in our minds. We're like, oh, look at that wave, right? But it's kind of funny that we all know what a wave is, since a wave is not actually a thing. It's something that's in perpetual motion. It's not an object that you could put on the table. It's a phenomenon. What is it that we're recognizing when we recognize the phenomenon known as wave motion? What we're recognizing is a situation where there's like these bumps, these weird distortion, these disturbances that are recognizable. Like when you say, oh, a crest is going down from left to right, and you like literally can take a stopwatch and measure, or even in Yankee Stadium, if everybody goes like up and down, and you can literally like say, oh, the wave is over there. Oh, the wave is over there. Oh, it took 5 seconds to make it across the whole stadium. And you'd be right? Like you can measure the time and space traversing of a wave pulse just as accurately, just as confidently as you can measure how long it takes an actual baseball to go across the stadium, right? But what is it that you're looking at? Like there's no thing. What you're looking at is a recognizable shape, a distortion from what is normally the case. Normally, everybody's just sitting in the stands like this. When someone stands up, you're recognizing, oh, they're out of orientation. And then they sit down. So you watch that ripple of disorientation, of disturbance, of distortion. Like that, what a wave is a recognizable disturbance from orientation. And what we're saying here is the rate at which so if you look at a wave at any point in time, at any point in space, or even more strongly, every point in time, every point in space, the rate at which the disturbance is becoming undisturbed is literally directly proportional to the amount of the disturbance. That's wild to me. You can tell. I mean, right? I mean, that's what a wave is. Something that's restoring itself at a rate that's directly proportional to how unrestored it is. It's literally harmonic oscillation, but blown up into an extra dimension of space, at least one extra dimension of space. Okay, so that's what's going on here. Now we are going to end soon. That still doesn't tell you anything about the Doppler effect, I know. But first of all, but there will be questions about that on the final. So what you want to know ultimately is in English, what I've just said, and you can write this down as a takeaway that you either do or do not understand. But the takeaway of everything I just said in English is wave nature. The nature of wave motion is acceleration is directly proportional to concavity. That's what the wave equation is saying in English. At any point in space and any point in time, therefore every point in space, every point in time, the acceleration of that piece of the medium is direct back home to equilibrium. Acceleration back home is directly proportional to concavity, to distortion from home. Okay. Okay. A couple more quick things I have to say. There'll either be, as I say, the next video that I post may be one from last semester, so it may be slightly discontinuous from what we're saying right now. Again, but just remember, the goal of all this is to get us into Doppler effect. That's where this is all heading. I'm going to say a couple more quick things right now. Okay, yeah, just let's keep looking at these pictures. I know we're looking at the same picture for a million years. Well, look at it. I will flip the page, but look at the top two pictures. Look at the second one first. What you know already from simple harmonic oscillation is that the interval between any two like points in a phase, like from the interval between two crests, or the interval between two troughs, or the interval between two corresponding points in phase, that interval in the second graph is an interval of time, right? Because in the second graph, or in the third graph on the page, whenever you're just looking at one oscillator going back and forth in time, the interval between two crests on the cosine graph is a full cycle of time. It's the full amount of time that a cycle takes. We call that the period, right? Capital T. It's the period of time. The period is the amount of time that a full cycle requires. Well, similarly with a wave, if you draw the other picture, if you draw the y versus x graph for a given moment of time, we can make a similar claim or a similar piece of identification that the interval between any two similar points in space, like two crests that you can actually now see with your eye in space, it's not a time now, it's a space, literally a space. It's the length of a cycle as opposed to the duration of a cycle. That length of the cycle we designate with a lambda, and we call it wavelength, length of wave, right? So almost done. Okay. So what we're now saying, we're saying acceleration is directly proportional to concavity, right? We're saying the constant of proportionality is this omega over k squared, this angular frequency over angular wave number squared. So what's that all about? What is that constant proportion? Is it just a constant? Is it meaningless? No, I think it's pretty meaningful, actually. Let's talk about what it is. So let's unpack it. omega by definition, well, omega was angular frequency, right? Number of cycles per time, right? That's what for each individual oscillator. That's what omega was. So omega by definition equaled that 2 pi over the period, right? Radians per second. That's what omega was. Sorry. What was K? Or what is K? K is the newer concept. K is analogous to omega. We remember again, we didn't have a K when we were talking about an individual oscillator because an individual oscillator wasn't spread out in space. It just went back and forth in space. Individual oscillator was a spatial function of time. Then we put a whole bunch of them together, and now we get this wave pulse that is a spatial function of both time and space, right? So then this other thing, this analogous counterpart got introduced, this rate of cycling, not just in time, which is what omega is, but this rate of cycling in space. So what is that? Well, that is this. Right? If angular frequency is the number of radians, the number of cycle portions that we do per each unit of time, if angular, right, and the inverse of it is like how much time it takes us to do a cycle, et cetera, et cetera. Well, K, angular wave number, is the same idea, but applied to space. So it's 2 pi per lambda. Oh, and I'll say again what I just said on the other page, but I didn't really write it clearly. Lambda, it's called lambda, and it stands for what we now call wavelength. It is the full amount interval of space for one cycle. It is measured in meters, just like capital T is the full duration of one cycle, right? It is measured in seconds, right? So this is all like a big analogy. What we're ultimately always saying is what a wave is harmonic oscillations in time and space at the same time. I mean, it's the more you think, well, the more I think about it, all I can say is all I do is think about this 3 times a day for 30 years, and it only gets more interesting to me, not less. I mean, that's got to tell you something, yes, that I'm crazy or very limited in my imagination. But really, there's so much going on in any given wave pulse, so much going on that it can exist without actually being a thing. I mean, what more really do I need to say? Well, apparently a lot, because if this is true, if omega, and we're going to wrap up very shortly for anybody who's interested to know. But if omega is angular frequency, and if K is angular wave number, then omega over K by definition, well, by substitution equals 2 pi over T all over 2 pi over lambda, right? And the 2 pi's cancel. And, when you divide by, so it's now like 1 over T divided by 1 over lambda. That looks very annoying because it is. But what that really is 1 over T times lambda over 1, right? So what, to divide a fraction, you multiply by the reciprocal. So what omega over K is actually is lambda over T. And in units, that means meters per cycle. Here, let me be really clear about it. What is that? That's meters for a full cycle over seconds for a full cycle. And I'm just writing the full cycle out to be explicit or to remind you what we're saying. But what we're saying is omega over K is the number of meters from crest to crest per the number of seconds that it takes to get from crest to crest, right? So if you're standing, if we were talking about a two-dimensional wave, a water wave here, just for, well, no, if you're standing in the lab and you're seeing these pulses go back and forth on the string, if it turns out that there's 3 meters between every 2 successive crests on that string, 4 meters between every 2 crests, and if you have to wait 2 seconds from one crest to the next crest, so there's 4 meters between the crests and you have to wait 2 seconds from one crest to the next, then that means that each crest is traversing 2 meters per every second. In other words, as I know many of you were saying things about this in the chat yesterday, and I was totally happy, like very excited to see that, and it totally noted and recalled, and please submit to Tom Nook for points. What we're saying is the omega over k is the speed of the wave. And we're just about done, at least for today, for now, but just about. But let me really emphasize the wave speed. Now, let's back up for a second. There's all these derivatives happening. There's like acceleration over here, and there's concavity over here. And isn't acceleration the derivative of velocity? So you might even say, if you're really thinking, you might say, wait, I thought at every single place, isn't like the velocity constantly changing, and isn't it getting faster and slower and faster? Yet that's all of oscillation. Oh, yes, there's vertical V's and vertical A's happening, going continuously, flipping around all over the place on this thing. But what this is the wave speed. This is the speed of propagation. This is the speed at which pulses flow along the x-axis from one place to the other, right? And right, so omega over k is the speed of propagation. In other words, what a wave is at any given moment in space and time, any given point in space and time, the acceleration of that point back to equilibrium is directly proportional to the concavity of the medium at that point. And the constant of proportionality is the square of the speed at which these pulses flow. I mean, that's an amazing amount of information that's an amazing number of descriptives packed into one freaking sentence. And one sentence is we're basically just saying y equals mx plus b and b 0. Like when you, I can't emphasize enough, the wave equation captures all of these properties of waves and ties them all together in one little package. And it's like you can write it in one line. The only requirement is you have to take like 3 levels of calculus in order to read the symbols. But maybe it's a good reason to care about calculus. But what I'm saying now, and I'm really almost done, even though I'm always lying when I say that, what I'm saying now is, okay, omega over k is the speed of propagation of the wave. But the most profound thing I need to say about that before we close, I'm sure you're with me. You're with me, right? Catch up. Okay, do you want me to turn back? Do you want me to turn back page? Okay. That was weird, right? If even one of you was just thinking that, then like I know who you are. No, okay. 1, 2, 3. Oh, you needed that page? Okay. Well, my handwriting, because I look like an axe murderer. Oh, I also do look like no offense, if there are any axe murderers in the room, I don't mean to. You have a special place in my heart too. Just I hope that you're as inefficient at your crimes as I was at physics when I was learning it. This says omega over k squared is the proportionality constant between acceleration and concavity for any and every point in space and time in a wave. That's what this says. Okay, we really are done. And then there's that. And then there's that. Now, here's my big last final point. In a way, all we've done today is unpack the meaning of the symbols in the wave equation. In a way, I'm just trying to translate the wave equation in English. If you're following this at all, part of you might be thinking the entire time that you knew this the entire time because you knew the symbols. But when you step back and look, maybe you're realizing that we're saying it in a way that you hadn't consciously thought of before, or maybe not. But the last thing I have to say is, if the constant of proportionality is the square of the wave speed, right? And then, yes, indeed, that is my big point. If this business is the speed of flow, the speed at which crests and troughs, distortions are flowing back and forth along the equilibrium axis, the propagation axis, if that's what that is, let's note This is you could watch videos about this too if you want. I made a huge point about it once. I yelled about it. I said it was important, but it would have been very reasonable to wonder why I thought it was so important. I just kept saying it was really cool and surprising. Let me read this. It says, remember, from our study of simple harmonic oscillation, omega, angular frequency, is not a function of amplitude, right? In this case, amplitude would be Y naught. It could be X naught. It could be capital A. But angular frequency is not a function of amplitude. It's independent of amplitude. Remember, angular frequency is not determined by how you set up any initial spring. It doesn't matter how far back you hold any initial spring. And since K is the space counterpart to omega, anything I'm saying about omega ultimately applies equally to K in this context. So what I'm saying in English is that omega is not determined by how you set up these oscillators. It's only determined by the measurable intrinsic properties of the oscillators, specifically, for example, stiffness and mass, right? Omega, remember, omega was square root of K over M for a mass on a spring, or it was square root of G over L for a pendulum. It's whatever it is that has nothing to do with how you set up the thing. It just has to do with the ingredients of the thing itself, parameters, constant material properties of in this case, medium. So every time I use the word medium, what I mean by medium is the material collection of oscillators. The medium is the material. The big group of particles that are going back and forth, like in the case of your lab 3, the medium is this long metal spring. You have a bunch of little pieces of metal that are going up and down in order to create this wave pulse, right? So what we're saying here is omega and K are fully fixed by the properties of that medium, by how massive it is, or in this case, how dense it is, how much tension there is in that metal. And if we were talking about like sound waves in air, we'd be saying that the omega and the K fully depend on, say, the temperature of the air and the pressure of the air molecules in relation to one another, right? So we're saying if omega and K are fully fixed by parameters, that, okay, I'm just about done. Sorry. Wait. Give me 1 second. Yes, I'm sure, but we have to check with them. Give me 1 second. Hold on. Wait, just 1 second. Just 1 second. Well, we definitely are about to wrap up, but this is the wrap up. If omega and K are fully determined by parameters, if they can't be affected by what you do to the oscillators, they're only affected by the intrinsic measurable material properties of the oscillators themselves. And if the medium is just that group of oscillators, the medium, whenever we say medium from now on, we mean the actual material, the bunch of masses on springs of whatever type that is ultimately going to oscillate in this pattern of patterns in order to allow a pulse to go through it, then this means V is entirely determined and fixed constant relative to the medium. This is the last thing I'm going to write. I'm putting down the pen. I'm putting down the cannoli. But what I'm saying, but this is huge. I'll just highlight the whole page. What I'm saying is one of the reasons we love waves, besides the fact that they're so weird and immaterial, is that once you have a wave, once you have a bunch of oscillators lined up to create a pulse going through it, each oscillator can only oscillate at a rate that's determined by what it is, not anything we do to it. And then the speed at which the pulse propagates through the wave is fully determined by those oscillation rates, right? The speed of the wave is omega over K. Omega and K, you can't do anything about once you get these things going. So wave pulses necessarily travel at a speed that doesn't accelerate or decelerate, each wave pulse necessarily travels at a rate that is constant while it's traveling and constant and fixed by the medium. Like, it's not just constant, it's predictable. When people talk about the speed of sound, the reason they can even say that at all, what they really mean is like the speed of sound through air at standard temperature and pressure. Like, they're tacitly specifying a medium in their mind when they say the speed of sound, but they're right to do it. Once you specify the medium for a wave, once you specify air at this temperature, or water at this depth and salinity, or metal at this tension and this density, whatever it is, once you know the medium through which you're going to send pulses, the pulses have to go through that medium at an unwavering and fully predictable, fully fixed assigned speed relative to that medium. So sound always travels at 340 meters per second relative to air, as long as it's traveling through air that is at standard temperature and pressure. Bottom line, and we are done, but this is huge. This is why the Doppler effect, if you want to get started on the homework for tomorrow, and no matter what, I'm going to post more videos, but there already are videos called Doppler, like all throughout the old semester. I mean, that's what you're looking for. Any video that has the word Doppler in it is what you want to look at next to help you with the homework for tonight. But the bottom line of this is, we're saying, if you ever look at waves at all, whether it was in lab 3, whether they're easily created or naturally created or whatever, you look at wave ripples in any dimension, and here's a really simple, obvious thing that you've known your whole life, but you might not have consciously noticed. If you look at wave ripples in a pond or on a string or whatever, you will notice one ripple never catches up to another. It's like so duh, but it's so not duh. Ripples can cross if they're going in opposite directions, but you'll never see one ripple start catching up to another and like overtake it or pass it, or right? In fact, there's always an equal space between ripples. Hello. Siri's now getting involved. Or Mrs. Google. They have such a rocky relationship, don't you find? One ripple will never catch up to another ripple. It'll never drag by another ripple. One ripple is always an equal space away from another ripple. We're about to end right now. You can tell because I'm yelling. And that equal space is what we call a wavelength. Why are we even able to talk about a wavelength in the first place? 1 second, because waves always travel at the same speed in a given medium, and we can know what that speed is in advance. They're so predictable. They're so reliable. They're so smooth. They're so useful. They're waves. Adopt one, please. Thank you. Good night. Okay.